Swayam Prabha. Digital India. Educated India.
This maritime engineering, as you see, is a very special program which has got multidisciplinary input from mechanical, civil, structural, aerospace, naval architecture, chemical engineering, electrical, electronics, applied mechanics. It's a multidisciplinary program. You will find this program is completely different, dedicated to industrial training and thorough capacity building on the new trade of maritime sector. It's a grooming economy which will give you a lot of job opportunities and research frontiers as far as India is growing. And the Blue Corridor effect, which is planned by Government of India, is one of the important mission which requires maritime engineering growth to happen in the country. So this program caters to expected that capacity building in this program.
Friends, this is part of a material science engineering laboratory which becomes one of the teaching aid for the maritime engineering program. So when you talk about materials innovation in maritime industry, though concrete and steel have been conventional candidates of choice for engineers, for example, we have titanium vessels, high-speed craft boats made of fiberglass. These are all advanced materials which actually do not come across conventional standard design code of practices. We conduct box furnace test, tube furnace test, vacuum arc melting, induction melting, vacuum induction melting, vacuum sealing unit, which are all present in this laboratory is a small segment of material science laboratory. Friends, a typical furnace where the operating temperature for testing specimen can go as high as 12 degrees Celsius. Generally at room temperatures and ambient condition, the mechanical properties will not alter much. As you see in the course lectures, you will notice that strength of the material get degraded when the temperature rises beyond 600. Therefore, when you talk about fire resistant design, you must also choose an alloying element such a manner that the strength doesn't degrade beyond 600 degrees Celsius at all. Welcome to the ambience of IIT Gandhinagar Lecture Theatre. This is one of the interesting classrooms where the maritime engineering classes will be conducted. We have got state-of-the-art projection facility and good audio-visual recording systems. Once the lecture is over, you see the system here. We can generate the PDF files of the lecture directly and you can email the PDF files directly to your email IDs. So it's a state-of-the-art facility we have in IIT Gandhinagar where the lectures are lifetime recorded and shared with the students immediately. This is the IIT Gandhinagar library. This has got all collections of books which are referred as the standard textbooks and references for the course and the program. It also has lot of online editions of design code of practices and reference materials and e-collections of various video lectures of international courses and programs related to maritime engineering. We will be taking you around to the advanced material manufacturing units. So you will have state-of-the-art facilities available at IIT Gandhinagar. So welcome to the program to join MTech and PhD at IIT Gandhinagar Maritime Engineering. So please try to enjoy and take the advantage of this to the maximum. Welcome to the program and welcome to IIT Gandhinagar. Welcome friends to the fifth lecture on the course Marine Renewable Energy Systems, where we are discussing about the analysis, design and development of renewable energy systems with a primary focus to wave energy converters, and of course we will also discuss about the offshore wind farm design and developments. In this lecture number 5, we will talk about the basics of the numeric analysis. We will talk about the basics. Okay. Now friends, as we discussed in the last lecture, wave motion is described using velocity potentials. Airy's wave theory helps us to understand this in a very simplified form. This theory actually uses linearized Bernoulli equation, assuming that waves are small in amplitude and large in wavelength. And we also assume the uniform water depth. It means the bathymetry effect are neglected. Okay. In addition, the theory assumes, or I should say also assumes, that the fluid is inviscid, irrotational, incompressible, and therefore it actually solves linear potentials. Of two waves, the diffracted waves and radiated waves. When these two happens, when a body or a wave energy system anchored to the seabed is interfered by a wave. So, during wave Beck interaction, this interaction produces diffracted waves and refracted waves. Okay, I need to solve this using a simple linear theory. Therefore, we refer this solution or the theory essentially as, so it is referred to as potential wave theory. Okay. Bernoulli equation, on the free surface, which conserves mass and momentum at every point in the fluid domain. Now, this is given as minus dou phi by dou t plus P A by rho plus half del phi square plus g eta is C. On the free surface, where z is eta of x, y and t. Equation number 1. Okay. In this equation, let us say phi represents complex wave potential function, Pa represents atmospheric pressure. Rho, density of seawater, which is approximately 1025 kg per cubic meter. It is slightly more than the density of water. It is due to the presence of mineral salts and other contents in water. Okay. Having said this, the linearized version applied the boundary conditions on the WEC, because I am looking for a simple solution for the WEC design. So, I apply linearized version of the above onto the WEC surface, and we consider that the WEC surface remains in equilibrium and instantaneous variation in the sea surface elevation is neglected. Instantaneous variations in the sea surface elevation is neglected. So, now instead of defining the equation on the free surface, where z is eta of x, y and t, we can define this on z as 0. So, in that case, minus dou phi by dou t plus Pa by rho plus g eta will now become 0 on z equals 0. We call equation number 2. Okay. So, as I said, P is the velocity potential and Pa is the atmospheric pressure taken as a reference for the pressure variation. Okay. And therefore, since Pa is atmospheric pressure, which is taken as the reference to mention the pressure variation, this can also be set to 0. On the free surface elevation of eta. Therefore, the equation now gets a change as eta now becomes 1 by g of dou phi by dou t at z equals eta. Equation number 3. Now, we also said wave amplitude is very small in comparison to the wavelength. Therefore, this equation now further becomes 1 by g of dou phi by dou t at z equals 0. Okay. Furthermore, we apply linearized kinematic boundary condition. Which is helpful to describe the component of fluid velocity normal to the structure, which we say it must be equal to the free surface velocity, because we are applying linearized kinematic boundary condition. Therefore, I can write this equation as dou eta by dou t plus dou phi by dou z is set to 0 on z equals 0, equation 5. Having said this, for a linearized version of the governing flow equation, the free surface boundary condition can be written by substituting the equation 4 in 5. So, we get this as dou square phi by dou t square plus 1 by g of dou phi by dou z is equal to 0 on z equals 0, equation number 6. Now, potential flow is solved by developing the Laplace equation with the boundary conditions such as free surface, body surface, far field and seabed. These are the boundary conditions we apply. The first three, that is 1, 2 and 3 are already given in the above equations. Okay. So, therefore, we need to satisfy the far field boundary condition, which states that the wave generated by WEC should die down far away from the WEC. Okay. So, the far field boundary condition states that the waves generated by the WEC should die down far away from the WEC. Okay. So, only the instant waves must be present. Only this must be present. Therefore, the literature suggests this decay in the form of radiation condition. So, this decay is suggested in the form of radiation condition, whose magnitude is inversely proportional to the square of the radius distance. And the wave number, which can be then written as P should be inversely proportional to 1 by square root of k r e to the power of minus I k r as r tends to infinity. So, we call this equation number 7. So, the total velocity potential of a typical wave floating wave energy converter is decomposed as follows. P total will be now sum of P incident, Ps plus Vr, equation number 8, where P total represents the total wave potential Pi represents the incident wave, Ps represents the scattered wave, and Vr represents the radiated wave. This is R, okay, this is Vr. So, friends, the diffracted wave is composed of incident wave, and the scattered wave. I should say now the diffracted wave is a sum of incident wave plus scattered wave. We all know incident waves are very calm waves because they generated from the source, which is wind generated ocean waves. So, they are calm when no structure interference happens to them. That is, no structure obstructs them, they are very calm. The diffraction field is disturbed when the water disturbed, when the incident waves interact with undisturbed structure. Now, in our case, the structure also responds and vibrates. The structure is also disturbed. Okay? So, at the same time, The radiated field is also created due to the structural vibrations. All is happening in calm water. Okay? All happens in calm water. Therefore, the boundary conditions associated with each of these potentials will have complexities. Okay? Since the waves are sinusoidal, with the process being linear, the decomposition is based on linear superposition of the effects caused by the incident, diffracted and radiated waves. Because we are looking for the assumption that the process is linear. Therefore, friends, the numerical tools used to solve the velocity potential and dynamic behavior of structure, combine them in solving these analytical methods is not practical. Therefore, we have three methods to solve such problems. So, such problems can be solved by three methods. What are they? One is a frequency domain approach. The second one is time domain approach. The third one is spectral domain approach. So, we will discuss about our formulation in frequency domain and time domain approaches. For understanding spectral domain, you may look into one of the reference textbooks which we suggested in the website of Swayam Prabha. We also say the solution will be dependent on the fidelity of the hydrodynamic model, therefore, the wave energy converter developer can choose the order of non-linearity in the analysis. Generally, this is chosen within the time domain. So, friends, we will discuss in detail about the frequency modeling or frequency domain modeling slightly in detail. For the wave energy converter development, one should have a rough idea about the overall geometry and technical aspects. So, frequency domain approach is the first step to understand the overall geometry and the dynamic response of the WEC. Then later on one can redesign the geometry and the system arrangements to harness it to the maximum. So, the first step is to find out this general behavior using frequency domain approach. So, the frequency domain approach gives us rough estimate. Please understand friends, I am very careful in making the statement. It only gives me the rough estimate of the absorbed power output. So, to get the absorbed power output, one can assume virtual linear power takeoff system. So, we already discussed about the power takeoff mechanisms in the previous lectures. Since frequency domain approach a linear model, all non-linearity is generated during the real wave structure interaction, specially related to resonance and extreme wave effects will be ignored. That is a very important statement here. So, all non-linearities arising from wave structure interaction especially near resonance condition and extreme wave condition will be ignored in this analysis. So, one can say that is a very serious limitation of this. But the advantage is it becomes very cheap and inexpensive in terms of computational effort. It is faster. So, one can get a rough idea about the absorbed power output by fixing a virtual linear PTO to the system and ignoring all non-linearities arising from such critical conditions. So, this will help us to understand this frequency domain approach helps us to understand the suitability of chosen geometry of the wave energy converter for a specific wave input, that is site specificity can be addressed. It will also help us to understand the resonant band width at which this need to operate. It also understands the effect of wave loads on the system, of course, that is a response. Then we try to obtain what is called the transfer function, which can be used directly to extrapolate the response behavior of the WEC system by varying the input conditions of wave loads. Therefore, all this will now lead to optimizing the geometry or the geometric design of the wave energy converter in terms of its shape, in terms of its size, in terms of its number and in terms of capture width ratio, all can be arrived later based upon the first set of results what we get by solving the problem in frequency domain approach. So, therefore, this analysis starts with the extraction of hydrostatic estimation of the device. So, the analysis starts with extraction of hydrostatic estimates of the device. It also helps in estimating the frequency dependent hydrodynamic parameters. Of the whole design. Hydrostatics can provide points related to the device stability, is recentering ability, it helps us to locate the center of gravity, the center of buoyancy, metacentric height, water plane area, submerged volume, overturning and restoring moments. So, these are vital parameters of output what we can get from the hydrostatic analysis. So, this will provide an appreciable input to the design of WEC. The hydrodynamic parameters will give us coefficients related to added mass, radiation, radiation damping, excitation force and response amplitude operator, which call as ROUs, of all degrees of freedom which are active in the system, assuming potential wave theory. So, we already said this is a linear theory. So, friends, both the power and the performance in all active degrees of freedom where the device is designed to harness wave are estimated by providing appropriate power takeoff properties. Okay? So, the power and performance of the WEC can be estimated by providing virtual linear power takeoff system to the WEC. Therefore, the output what you gain from this analysis is improved by iteration. So, what would you like to improve? You can improve the shape, size and other design parameters, that is mass concentration and so on. And this all should improve the hydrodynamic characteristics of the proposed WEC, wave energy converter. So, most of the time the frequency domain analysis of all commercial tools helps us to solve the response on 6 degrees of freedom. However, in wave energy converter analysis, it will depend only on the active degrees of freedom. Okay, mostly it is heave or surge for point observers. If you use point observers for modeling, it will be either heave or surge. So, the response will be applied only on the active degrees of freedom and not on all degrees of freedom. So, therefore, friends, the frequency domain approach workflow which can be used in ANSYS AQUA can be summarized like this. Let us say the frequency domain model. Will look like the device parameters which we assume like which can be obtained from 3D solid model, water depth, mass, inertia, center of gravity, center of buoyancy, etc. can be all obtained, which will become an input to the frequency domain modeling. Which can be done in ANSYS AQUA or in VAMIT or in NEMO. These are different softwares we use. Furthermore, the subsystem uses a linearized mooring model, which will help me to find out the stiffness and the unstretched length of the subsystem, which will also become an input the frequency domain model. Furthermore, I am also assuming something called linearized power takeoff system, which will help me to understand the damping and the stiffness, which will also become an input to the frequency domain model, and of course, the wave input like frequency and direction will also become input to this model. Let us see what are the outputs this model can give me. This can give me the excitation force, the radiation damping, and the added mass coming from the system. Okay, this can be obtained. Can also give me the response amplitude operator of the system. Let us also use the symbols, friends. Let us use the symbols here. Excitation force can be given as F E of waves. Radiation damping can be CR, and added mass can be AM of frequency dependence. Okay. So, it also gives me the response amplitude operator, which will help me to find out the mooring and PTO forces. So, they are coupled. So, they can also be an output, this can also be an output, can also give me the absorbed power, not the dispersed power, absorbed power of the system and the capture width ratio. So, now this will be helpful to post process and find the efficiency. So, friends, we will come to the summary of this lecture. In the summary of the lecture, we understand that the frequency domain approach, the time domain approach, the spectral density approach can be used to model wave, WEC interaction. But usually this interaction is modeled using a linearized wave we call potential wave theory, and this will help you to simplify and understand certain effective outputs which I want for design of the wave energy converter. So friends, I assume a system. For the system I find out the parameters, I assume a subsystem, I assume a linearized PTO. For a given wave input, I do frequency domain modeling using ANSYS Aqua, BAMIT or NEMO. I try to find the exciting force coming onto the system, the radiation damping which is required to in fact design the PTO. We do not know, therefore we assume linear, but it is not true. We also want to know the added mass effect because that can cause additional damping and friction to the PTO. So that becomes an output. We also know the response characteristics of the WEC under the wave structure interaction, and we also know the response characteristics of the mooring line and the PTO forces which will be an output from this model, and we also know the absorbed power of the assumed design, and we can also know the capture width ratio. So once this is obtained, to improve the efficiency, this can be again fed as an input data, and therefore this whole process becomes iterative. So that is the idea we have here at this moment, and that is how we summarize this lecture. Look forward for your presence in the subsequent lectures to understand further in detail about this. So this friends, this block diagram explains me the frequency domain model which is used as a first step in developing a wave energy converter. Hope you enjoyed the lecture. Please follow up these lectures on the Swayam Prabha course titled Marine Renewable Energy Systems, offered at Maritime Engineering Department at IIT Gandhinagar. Thank you very much. Namaste.